We are officially halfway through the semester in terms of the course material. We're halfway through. This is homework 5, right? We usually hit 9 assignments or 10 assignments. I'm hoping for 10 assignments this year. So we're almost halfway. It's gonna get more interesting, a little harder in some aspects, but you'll see that all the tools we've built up so far, from linear solvers to nonlinear solvers and the Taylor series truncation error, they are gonna be used in all the subsequent analysis that we're gonna be doing, okay? So in the chapter, in the part that we're gonna start today on curve fitting, you will see that we're gonna be needing linear solvers and nonlinear solvers to do further analysis on data, okay? But first, we're gonna start with Nate for the life hack today, yeah?
You want a free drink from Starbucks, you just gotta tell them that your first one was taken, and they put it on the little stand.
Okay. Okay, who wants to do, make sure, who wants to do Thursdays? Volunteers for Thursday's life hack? All right, Ian, okay, for Thursday. Okay. Okay. All right, if that works for you, you didn't hear it in this class, okay? I am not advocating. All right, good tip. All right, this, I really don't know what to say, but this part of the semester now, we started with like intro and error analysis. The next part was solving algebraic equations, which were both linear and nonlinear in nature. Now we're going to start looking at curve fitting. That's the third part. And under curve fitting, we're going to study interpolation and regression, and we might squeeze in integration to analyze data. Okay? So we will start with the easier one of those, which is interpolation. So that falls under curve fitting. And again, with every chapter, I like to start with learning objectives. So that helps you also fine-tune your expectations of the chapter. Hopefully at the end, you'll learn to define what it means to interpolate data. You probably know that. Derive the system of equations that one needs to solve in order to build what we call a polynomial interpolant. List the benefits and limitations of first-order interpolants. List the benefits and limitations of high-order polynomial interpolants. Calculate by hand an interpolated value using linear interpolation. That's the example we're going to start with, actually. Identify which points are best used with linear and quadratic interpolants. List the conditions for what we call cubic splines. You've probably heard of cubic splines. We're going to learn what they mean in this chapter and how to implement them and derive them in Python. Use built-in Python functions to perform both polynomial and cubic spline interpolation. Derive linear interpolation in 2 dimensions and create Python code to perform linear interpolation in 2D. So you have 2-dimensional data. We can interpolate those data as well in 2D. And then finally, if we have time, those 2 items in red, I add them this year, is perform linear interpolation with what we call arbitrary basis functions. So everything we're going to be doing, we're going to be using polynomials, x squared, x cubed. But what if you had data to fit with cosine and exponentials? So if we have time, we're going to do linear interpolation with arbitrary basis functions, and finally, nonlinear interpolations. In all of the above, you're going to see linear solvers, and in the last piece, you're going to have to do a nonlinear solver. Hopefully, we get there. Okay. The motivation behind interpolation is that oftentimes you are presented with discrete data that you've measured or someone else has measured over time or over a course of some experiments or some other independent variable that you're controlling. Okay? The idea would be, given those data, sometimes you want to find data in between the data points that you've measured. Okay? So let's say you're sampling every hour some temperature measurement at your house or some air quality measurement. And you kind of want to get an idea of what the value is between 2 points that you've measured. This is what interpolation allows you to do. Okay? I'll give you an example from my house in August. I measured the temperature in Fahrenheit over the course of an entire day, starting from midnight, recorded time 0 hours, all the way to the next day. So 25 data points really, but over a 24 hours. So starting with midnight, 75 degrees, then it starts going down the temperature all the way to 69 degrees at 6 in the morning, and then sun rises, starts warming up, 72 at 8 o'clock, at 10, 79, by noon, 86, and then at 2 and 4 o'clock you got maximum temperature at 91, and then 12, 2 o'clock, 4 o'clock, 6 o'clock, and then starts climbing down and continues the cycle. Okay? So suppose you have those data, and then I ask you, what is the temperature what do you think the temperature was at 1 o'clock, just given those data? So 1 o'clock occurs here between 12 and 14 hours, so that's 1,300 hours. It corresponds to this line. So what do you think the temperature is at 1 o'clock? Take a moment, and I'm going to introduce the spinning wheel of names. Spinning wheel of names to pick a name. So what we're going to do, we're going to spin this. Oh, okay. Ian, I picked the spelling from the from Canvas. Okay, so I saw your tag. Let me go back to the slides. Sorry, I have to figure out how to put the, yeah. So what? 87.5, 88-ish. Yeah, so somewhere between 86 and 89. Okay, more precisely, because 1 o'clock is right in the middle of 12 and 2 o'clock, right? A more realistic value would be exactly the average. Right? Exactly the average between 86 and 89 degrees, okay? Because it's right in the middle, right? Probabilistically even talking, that's kind of the best guess you could do, okay? And that's right, thank you. All right, so now I ask you, what is the temperature at 1:17 p.m.? So that's 13.28 hours along the axis. So you see, it's not in the middle anymore. It's kind of further biased towards the data point at 2 o'clock, okay? So take a moment and work as a group and tell me how you would predict the temperature given those 2 data points at 12 and 2. How would you estimate the temperature at 1:17 p.m.? Just describe how you would do it. Just describe how you do it. Okay. All right, what do you think? So what do you think, how would you do it? What would you do? Any takers? What would you do? 28. It's 0.28, yeah. Yeah. So you can take the weighted bias towards that side. Okay. I agree with that. Is there another way to present this idea? Okay. So I'm going to formalize that thought. You're exactly right, but I'm going to formalize it so that it lends itself to numerical methods. What I'm going to do, I'm going to draw a straight line between those 2 points. Okay? Find the equation for that line, and then evaluate that line at 13.28 hours. Right? And that will give me the temperature. Because that way, with the equation of that line between those 2 points, I really can get the temperature at any point between those two. Okay? So now go ahead and do that. Just draw a straight line between those 2 points, derive the equation for that straight line, and evaluate it at 13.28 hours. Straight line, ax plus b or mx plus b, right? That's the equation of a line. Find the slope and the intercept by hand. So the two endpoints, at 12 it's 86, and at 14 it's 89. Nice round numbers. Okay. Just find the slope, the intercept, and you got the equation for the line. And then evaluate at 13.28 hours. Okay. Pardon me? Yeah, it's becomes straightforward, right? Okay. Pretty straightforward calculation. You need another 30 seconds maybe? No? Okay. Straight line. The equation for a straight line is ax plus b or mx plus b. I don't know why they always refer to m as the slope. But first you define that equation, and I call it T of x because that's the temperature as a function of the hour of day. Okay. And then the slope is simply calculated by rise over run, so 89 minus 86 over 14 minus 12. So that's 3 over 2 or 1.5, right? So that gives you the slope. Next, you need the intercept. To get the intercept, b, you just evaluate, you apply that equation of the straight line at either one of those endpoints, either at T12, which is 86, or T14, which is 89. It's going to give you exactly the same value of the intercept b. I chose to do it at 12. So T at 12 is 86, but that's equal to m times 12. So because x is 12, right? And m is 1.5, which is what you obtained already, plus b. So it gives you 18 plus b equal 86. From that, you solve for b, and you get 68. Now you have the equation for that straight line between those 2 points. Next, all you have to do is evaluate now that equation really at any point in between. So if I evaluate it at 13.28, gives me 87.29. That's a reasonable value because it's between those two values, 86 and 89. And I don't expect to have some crazy solar heating in between those temperatures, right? So that's a reasonable value. Agreed? Okay. to state the obvious, this equation or this interpolant, we're going to start calling those interpolants from now on, is only valid between those 2 points. Only valid between those 2 points. If you try to apply it outside that range, you are not guaranteed you're going to get any reasonable data or any reasonable value. That's called extrapolation. Okay, outside the range of the data that you care about. Okay, so you just did linear interpolation. Okay, so now we're going to take this and generalize it. Given any 2 data points, again for linear interpolation, so giving any 2 data points, x1, y1, and x2, y2, by x, I'm referring to the independent variable, which is a variable that you are specifying, there you are controlling. And the y data are the response variables, whatever you're measuring. So hours of day, and the y variable was temperature, something you have no control over. Okay, independent variable, dependent variable. Suppose you're given 2 data points. The task is fit a straight line between those data points so you can evaluate it at any point in between. Right? That's our objective, is to find the value between those 2 points. So you just did it for a specific case of the temperature. Now I want you to do it for an arbitrary given data. So in terms of x1 and y1 and x2 and y2. Okay? So general case. You're given x1, y1, x2, y2. Derive the equation for the straight line. Again, same thing. Essentially, you want to find the slope and the intercept. Now, in this question, don't solve for the slope and the intercept. Okay, I want you to derive the equations that you need to obtain the slope and the intercept. So you could say the slope is equal to y2 minus y1 over x2 minus x1. But I don't want that. I want the equations that govern the slope and the intercept. So in other words, this line has 2 unknowns, m and b, right? And it's passing through 2 known points. So what happens if you apply it at each one of those points? You get 2 equations with 2 unknowns, right? So derive those 2 equations. I know you know how to obtain the intercept. Okay, but that's not what I'm after. I'm after the system of equations that you can develop to derive the intercept and the slope. Okay? Because once we go to higher order polynomials, you can't find the coefficients that way. You have to build a system of equations. Okay, so here's how I'm going to do it. This line passes through x1, y1, and x2, y2. So those are 2 given data points that are given to us. We know those data. In the equation of the straight line, I have 2 unknowns in red. The slope, m, and the intercept, b. Because this equation, this line, is going to pass by definition through x1, y1, and through x2, y2, all I need to do is apply that straight line at those 2 points. That will give me 2 equations for the 2 unknowns that are missing, m and b. So in other words, y1, the value of that line at x1 is mx1 plus b, and the value of the line at x2 is y2 equal mx2 plus b. That's a system of equations with 2 unknowns. Yes?
Should the m and b be flipped around on the second one?
Yes. Yes. Thanks, Miles. Thank you. Good catch. Let's just do it. Yes, so that's the objective. We didn't learn matrices and linear algebra, linear solvers for nothing, okay? They all come back to all of this, okay, to haunt us. So that's a system of linear system, 2 equations and 2 unknowns. And if you invert that, which we can analytically, you'll get the solutions we obtained if you were to do the the formula for the intercept, etc. And one way to write it in this particular case is to do it this way. You see this is the slope, y2 minus y1 over x2 minus x1. Y is the equation of the straight line. So that's a general simple formula for linear interpolation between 2 points. If you're fitting a straight line between 2 points, that's the general formula for linear interpolation. We call this a linear interpolant or a straight line interpolant. Okay? The advantages is that it's super easy to use. It's very convenient. It is always the first thing that I do when I have data in front of me.
I was going to ask, why is B Y1?
No, it's not y1. B is y2. B is minus mx1 plus y1. Right? So I factored it in. Yeah. There's an x1 in the parentheses. It's just a different way of writing that line equation. Okay? But it's still mx plus b. And b in this case is y2 minus y1 over x2 minus x1 times minus x1 plus y1. Okay? The disadvantages is that it is not very accurate if you think your response variable is very nonlinear. So what if you sampled at these 2 points? I sampled at 12 o'clock and then I sampled at 4 o'clock. But then in the middle, I don't know, something changed. There was a solar eclipse and the temperature dipped. Okay? So then it's no longer a straight line. It's something different in between the 2 data points. So in that case, linear interpolation is going to fail. Because you're missing data anyway, right? And even higher different order interpolation that we're going to learn about might also not give you a good prediction. Okay? So a critical limitation of linear interpolation is that it's not accurate for nonlinear functions unless you have a lot of data about that nonlinear function. And then you have very closely spaced points. And as the points get closer to each other, they're really kind of almost a straight line from each other. Okay? We didn't learn much so far, right? Because we have the tools, we know how to do this. But now the next step is to apply this linear interpolation for a large data set, like that temperature data set I gave you, or another data set that I used to, as an example in class, is the density of air versus temperature. Okay? So at higher temperatures, the density of air decreases, right? Air becomes lighter, that's why it kind of goes up. And at lower temperatures, in Kelvin here on the x-axis, the density is higher. So the units here, kilograms per cubic meter. Okay? And then if I were to ask you that same question, what is the density of air at some arbitrary point in between those two measured, in between those measured data points? If you're doing it by hand, you would have to find the 2 data points that are around the point in question, like we did with the temperature data, right? But if you have a huge data set, who wants to go and try to find the 2 data points and do linear interpolation in between? Wouldn't you wish there was a way to apply linear interpolation once and for all for an entire data set that could have 1,000 points in it, and then just reuse it as needed? Okay? This is exactly what we do with this procedure, is that there's a mechanism in Python that allows us to connect a straight line between each pair of points. Okay? So if you were to zoom in here, this is what's happening. Okay? A side note that I always like to give to my grad students and my students is that when we're plotting data, I always plot scatter data, points only. Don't connect them with anything, because the default connection mechanism in MATLAB, in Python, in Keynote, in Excel is a straight line between the 2 points, between any 2 points. And that might not be true. The relation between any 2 points might not be a straight line, might be a curve in between. So when you're plotting discrete data, first always plot it as a scatter, just points. So notice the previous one. Plot it like this. Okay? Don't draw connection lines to it. Okay? Now, I know here I'm doing linear interpolation, and that's how linear interpolation is going to look like. It's going to draw a straight line between each pair of points. There's a beautiful and simple mechanism in Python that allows us to do this. Okay? And it's based on a library in NumPy, or a function in NumPy called interp. Okay? So you call it from NumPy, you just say NumPy.interp. Now, interp takes 3 arguments at a minimum. Okay? What I call xe, xi, and yi. Xi and yi are your input data. That's why I put an I there. So in the case of the temperature and hours of day, xi is the hours of day, and temperature are the yi's. In case of density and temperature, temperature is your xi data, and density is your yi data. Okay? Xe is the value where you want to interpolate. And it's also a user-provided value, right? I want to interpolate those data at 13.28 hours or 13.6 hours, okay? That's also an input to the function. Now, this interp takes an array for xi, an array for yi, or just one, or just a pair of points. Doesn't care. It's going to go and weave a straight line between each pair of points. Xe could be an array of points, or could be a single point as well. It doesn't matter. The value of the interpolation, the evaluation of that interpolation, is your return value, which I call ye, okay? Which is the interpolated value at xe. Okay? So let's get our hands wet with this. Go ahead and download this interp activity 1 with gaps notebook from the interpolation module on Canvas, and we'll work through it together. Okay? Okay, so interp activity 1 with gaps. Okay. This is what you should be seeing. Okay, and should have all of the building blocks necessary to do this problem. Can you all see in the back? Thank you. Okay. So maybe we zoom in a little bit. So go ahead and execute the first cell. And there's a little description over here. And I already typed in the data for you for density versus temperature. Okay? Those data, just kind of put them in for you. In your homework, I'm going to give you those data as a list in the PDF. So you have to copy and paste them in Python, just like I'm doing here. Okay? Now, the first thing to do when presented with data is to get familiar with it. So when in doubt, print it out. When you have data, plot it. Okay? Get familiar with it. Flirt with the data. Okay? So let's see what this data is doing. I want to plot the temperature, T, or the density, rho, sorry, versus the temperature. Okay? So on my x-axis, I want the temperature. And on the y-axis, I want the density. You can type \rho and press tab. It will convert it to a rho. Okay? Then when I plot this, this is what I get. Okay? Now, note that I focused on making this a scatter plot. And the way I did this, I forced it to do a symbol here. okay? If I didn't put a symbol, it would have defaulted to doing it a what? A collection of straight lines. Line, you see here, and then another line. You see how it's jagged? Okay? So you could do, to enforce that idea, you could do KO dash, and you see how it's weaving the points together. But always start by plotting your data as a scatter, okay? Are we there? Okay. So now we have these two arrays. They are our input data, T and rho. Okay. Now, always plot as a scatter. However, to see what linear interpolation does is essentially you just do KO and dash, and that will give you what a straight line looks like. Okay, so this fills in this one, T rho, and then you do KO and then dash, for example, and then that connects them. This is what linear interpolation looks like. Okay. Now, using NumPy's interp function, find the density at 132 Fahrenheit. Okay, so I think I got the unit. I think the units are messed up. This should be 132 kelvins, actually. Okay, so I'm going to move this over here. Where is it? I can't find my cursor. Okay. So remember, this was the API or the function format for interp. Okay. Xi, Yi are the input data. Xe is where you want to interpolate the data. Okay. And Ye is the return value. Okay. The temperatures are actually in kelvins here. So just do it on Kelvin. Okay. So the input data are in Kelvin. Okay. So you don't need to do any units change. Okay. So go ahead and try it. Compute the density at 132 using the interp function. You can give it the entire data set. That's the whole point of it. You don't need to give it the 2 points, okay, around 132, right? Okay, that's cool. Yep, you get a value. 2.7, yep, kilograms per cubic meter. Now double check that that value makes sense. Look at the data and see if the value makes sense.
So are these values going to be the same as what we put in here? The T
yes, those are your input values. Yep.
Okay, so those are just the same.
Yep. So T rho. Yep. This is only showing how to do it in a different way. So yeah, KO dash, and then put a dash so that it's just. Yep. Yep.
Okay.
You're right. Yep. Okay. So now you're gonna get a value. Some of you are getting 2.77, right? Double check that value that it makes sense. Okay, look at the data and make sure that the value makes sense. No, it's Kelvin, all Kelvin. No translation, that was a typo. Yeah. Well, yeah, last year they gave me a hard time over that. Okay, so let's do it. Interp. Again, if you forgot that function signature, just press Shift Tab over here, and it tells you X, XP, and FP, and then explains things to you. Sometimes it's more mysterious than the way we explain it in class. What I know is that the last two values are going to be the X data and the Y data. In this case, my X data is T, and my Y data is rho. That's all I need to. I give it the entire data set. I don't have to worry about giving it the 2 points that are around 132 Kelvin, okay? And then I provided with 132 over here. That's the value of the density at which, that's the value of the temperature at which I want to evaluate the density. And it's not in the input data, okay? So if I run this, it gives me 2.77, okay? And for 132, that makes sense, right? So my starting point is at 100, I have a density of about 3.5. And then at that point, which is, I think, 150, let's see, what is the second point? Okay, so it's 200 at that point. It's going to be like 2.4 or something. Then 2.7 is somewhere around here, which can just totally makes sense. Okay. Now, I ask the question, find the density or the list of densities. Okay, let me call it the densities at all of those points, 123, 251, 443, 599, 602, and 899. Okay? All of them in one shot. Don't call interp for each value. What if you provide this entire array as an input for XE? It's going to evaluate it at each one of those points and return a list of densities at all of those points, right? Again, that is the objective of programming. If we had to go through each point and call interp again and evaluate, that wouldn't be an effective use of these vectorizing features in Python. Okay? So if you were to give it all of those temperature values for XE, it's going to return the densities at all of those. You got it? Okay, now plot those points on the plot as red dots. For those of you who got it, go ahead and put them on the plot. Okay, so here's how I would do it. XE is simply, I'm just going to copy and paste these values over here. Okay? It's a list of temperatures. I want to find the density at each one of those temperatures, okay? So if I pass this to interp, still giving it xi and yi as the density, as the temperature and density, then it's going to return a list of densities at each one of those points. 2.99 is the density at 123, 1.39 is density at 251 Kelvin, 0.78 is the density at 443, and so on. Okay? Now, to double check that these data make sense, go ahead and just plot them on top of the original data and see if they fall in between. Okay? So here's a plot of the original data. Now, go ahead and plot XE and YE on top of that plot. Okay. 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 Very good. Okay. 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 You got it? Fair and simple. Do they make sense? They do. XE, then YE. Right? If I do that, oh yeah, look at that. All my interpolated values, they fall in between their respective data points. Okay? This data point in particular is very close to one of the input data points. And if you were to choose one of the input data points, it's going to return the input value at that input data point. Okay? Because that's how the interpolant is built. Right? Okay. Let's see. All right. So now, I want to evaluate this interpolant at more points in between that temperature. So the temperature values, we only had 20 points of those temperature values. Those were measured. I want to now create a more smooth representation of the data. Okay, so I'm going to interpolate the whole thing I'm going to create more points between 100 and 1,000. I'm going to create 100 points between 100 and 1,000. It's just a bunch of other temperatures. Okay, I'm going to evaluate that interp function and then plot it. Okay, some of you already did that. So if I were to create a lint space from 100 to 1,000, so that's going to give me a list of temperatures, 100, and whatever, 110, 120. Emily.
Would you ever consider using XE0 to XE-1?
That would be extrapolation. And that would fall outside the bounds of the data. And there's no guarantee on the behavior, right? Because you really haven't sampled there. You don't know what the physics are going to look like. And so in this case, it would be unphysical, right? Because there's no negative temperature, right? And you might end up with like negative density. So
Just for like the end space, inside that.
Oh, for the temperatures, you mean T0 and T-1? Yes.
Yeah.
Actually, that's a great idea. So what Emily is suggesting, sorry, I misunderstood the question. What Emily is suggesting is like, well, crap, I forgot what the bounds of my data are, right? So rather than hard coding 100 and 1,000, I remember those data because I created them. But like, if you're like, you collected the data a year ago, right? You don't remember it. An easy way to access the bounds is to access the first and last entry of the temperature array or the X data array, okay? And what Emily suggested is we do T0 over here and then T-1 over there. If you're in doubt, print it out. T0 is 100 and T-1 is 1,000. That's exactly what we want, okay? I want to put 100 points in between, and then I'm going to interp temperature and density to all those points, and then I'm going to plot everything. Look at that. I have a nice, smooth data set, okay, from the interpolated data. It is not creating new information for you. It is not increasing the accuracy of your information. It's just taking the information you already have and fitting a straight line and finding the values in between. It's not a substitute to sampling, okay? Could you be missing something that might have happened in reality? Absolutely, okay? But it's still a very good representation of your data. With an interpolant like this now, you treat this interpolant, it's a bunch of straight lines connected to each other, right? That's what it is. It's a large number of straight line equations, but then you carry that and just reuse it later for other purposes, right? Okay, that's it for linear interpolation. Okay, so now, suppose now that you want to find the temperature given a density value. So now I'm going to flip that graph. Okay, imagine I'm plotting temperature versus density. So let's say you go and you can measure density of air somewhere, and you're like, okay, what is the temperature for that density value? You can infer the temperature because there's a one-to-one correspondence between density and temperature. You want to be able to infer the temperature from the density value. So one could say, let's just swap those two arrays. We have an array for temperature and an array for density, right? If we swap the arrays, treat the density as our x values and the temperature at our y values, then we should be able to find the temperature given a certain density. Okay? So let's read the statement here. Suppose that you want to find the temperature given a density value. For example, find the temperature at which the density of air at atmospheric pressure is 2.3364 kilograms per cubic meter. From the tabulated data, this should return exactly 150. Because at 150 kelvins, the density was 2.3364. Okay? So now let's try to see if interp can return that value, the inverse. Okay? So what I'm going to do, I'm going to invert this here. I'm going to put my x values as rho, okay, and my y values as t. And I'm going to evaluate at a density of 2.3364. Okay, run it. What did you get? 1,000. Does not make sense at all, right? It's 1,000. Right? Doesn't make sense because at 1,000 degrees, the density is almost half a kilogram per cubic meter. So what's going on here? For linear interpolation, do you have a question? Yes?
Shouldn't the t in the row be switched?
No, that was the first problem where we treated t as the x data and rho as the y. Now I want to do the inverse interpolation. Okay? For linear interpolation using the interp function in Python and MATLAB and whatever software you're using, for it to work properly, the x data needs to be sorted. Okay? Sorted from small to large. Okay? And that's the problem over here. So for linear interpolation to work, the values of the independent variable or the x data, they need to be sorted out. So if I were to plot the temperature T to print it, it is sorted 100, 150, all the way to 1,000. But for the data, for the density, it is the other way around. It is sorted from high to small. And that's the problem over here. Is that for this interp function to work, your data needs to be sorted from small to large. Okay? So it turns out that we can easily sort data in Python using 3 functions. Okay, let me go back to the slides where it's easier to explain this. Okay. Warning that the abscissae need to be sorted in increasing order. You can use these 3 functions to sort any one-dimensional array in Python. The first one is called Arcsort. You give it an array, and it returns the indices that would sort an array. Okay? So this would be useful when you're sorting multiple related arrays. We'll talk about that in an example. np.sort just sorts an array, gives you a new array that's sorted. And np.flip upside down flips an array upside down. So if it's increasing to decreasing, it flips it from decreasing to increasing, or whatever it is, you know, in this order, it flips it around. Okay? So you can use those 3 functions to manipulate arrays. Okay? So for this problem, I actually need the Arcsort. Okay? Before we get there, let's just try them out. Okay? So if I were to do np dot sort, give it the density row, then it flipped it around automatically. Right? The previous array was given in that order. Now it flipped it around. It's sorting it by increasing order. And in this case, this has the same effect as flip upside down. Okay? Because the density was monotonically decreasing. It didn't like change sign. But for my problem, while I need to sort the density in increasing order, I also need to sort the temperature so that each 2 points correspond to each other. Right? The best way to do that is via Arcsort. Okay? Arcsort is a little bit interesting, because it doesn't return an array, it returns the indices that would sort an array. So let me give you an example. Let's say my array is dot array, let's say 1, 2, 4, 7, 6, and then 3, and then 1. Okay? So on purpose, I created a non-monotonic array. Okay? It goes up in values and then goes down. Okay? And let's say I have another array, np.array, that goes hand in hand with this array. Okay? So they're one-to-one values. And let's just put in some random values, 33, 22, 11, 77, 66, and 12. Okay, let's see. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Suppose that those go hand in hand. The value at 1, 33 corresponds to the value at 1, 22 corresponds to the value at 2, 11 corresponds to the value at 4, etc. Now I want to sort this array, but I also want to sort the other one so that the values are consistent with each other. Okay? If I were to just do np.sort A, I didn't define. Okay? It's going to sort it correctly. Okay, let me pick another value over here, 1.3, let's say. Okay? It's going to sort it correctly, but how the heck am I going to sort the other one so that the values still match? The only way to do it is with Arcsort. Arcsort gives you the indices that would sort an array. So if I were to do np.arcsort A, it returns only integers. In other words, and those integers correspond to the indices that would sort the array. The first index is 0, so clearly 0 is going to be the first entry. The second one is 5. It's this guy. So it tells me, oh, the second one to sort this array is going to be array at 5. And then the third one is going to be at 1. The fourth one is going to be 3, right? And the index, so it's giving me the indices of the values that would sort the array. Okay, so now what do you do with the indices? You just apply them on the array and it would sort it. So check this out. I call this IDX. These are the sorted indices. IDX for index. So these are the sorted indices. Okay? And then all I have to do is say A IDX, and look at that. A applied with this index set will list the array, will return the array at that index set. And here's the punchline, is that index set, I can go ahead and use it on the dependent array. So now if I go after B at IDX, it's going to sort it so that it still matches this one. So 33 corresponds to 1. 12 corresponds to 1.3, right? So now it sorted the data in a consistent manner. That's probably the last thing we're going to learn in new thing in Python, and then we have plenty of tools moving forward.
How does it know to match?
It doesn't know how to match with B. When I did the Arcsort, when I did the Arcsort, I returned the indices that would sort that array. Any dependent array on that, I can just call it on those indices, and it would return them in the right order. Okay? Now that's what we have to do. So then, for the density, I need to get the arcsort of it. So IDX gives me the sorted indices of the density. Then I create a new array called row sorted, which is going to sort row according to these indices. And then my new temperature, according to this new sorting, is T applied at these indices. Okay? Check this out. Now we have a consistent set of data. Density and temperature, sorted according to each other. In this case, it looks like it's increasing and decreasing because the function is monotonic, right? So we just got lucky here. But it sorted the temperature. The point is that it sorted the temperature according to the sorting of the density. Now I can call interp on the sorted arrays. Okay? And look at that. It should return 150 exactly. And it does return 150 exactly, as we expected. Okay? So in the homework, I'm going to give you messed up data. Don't sort it by hand. Use Python to sort it. I'm going to give you like 2,000 data points that are all messed up. There's no way you can figure it out by hand. Okay? So you're going to just do Arcsort and just do that. Okay? All right. How about we take 3 minutes, get some water, stretch our legs.
trying to see. So obviously this x is like this x, but then b is composed of these things.
Yeah. So if you expand this, it's going to be y2 minus y1 over x2 minus x1 times minus x1, right? So just multiply this across these two, right? This whole thing times this whole thing, right? So this is just one, this whole thing multiplies x, and then this whole thing multiplies x1. Okay. So that x multiplies all of that. Now x1 minus x1 needs to multiply all of that. x1 minus x1. What? No, no, no. Times y. Okay, yeah, y2 minus y. Sorry, I thought it's 1 over 2. Sorry, yeah, that's right. Yep. Over x2 minus x1. Plus y1. Yep. So that would be b. That whole thing is going to be b. So when you solve, it's a 2 by 2 system of equations. You can find the solution, on Wikipedia, right? And this should be, this should be flip bm. Sorry about that. Yeah. All right. So don't forget, there's a quiz today. You can take it until 8 o'clock. And there's also the feedback survey on nonlinear solvers. So we'd appreciate feedback questions. We'll discuss those on Thursday on errors, linear solvers, and nonlinear solvers. The next step now is to go after higher order interpolation. Okay, we did a straight line now between the 2 points. But the question is, could you fit other things than a straight line? Absolutely. Okay. First definition is that an interpolating function, whatever it is, be it a straight line, be it a parabola, be it a cubic polynomial, be it a sine, cosine function, any interpolating function, by definition, when you hear the word interpolation, an interpolating function must pass through each and every point of the input data. That's why I asked you when to do the straight line to generalize it, to pass it through point x1, y1, and x2, y2. So that gave us 2 equations with 2 unknowns. Now we're going to take that and apply it to all sorts of functions, okay? Starting with polynomials. So, if you remember, with the straight line, now I switch the nomenclature. Instead of mx plus b, I'm using a0 plus a1x, okay? There's a reason behind that madness, okay? And then with two data points, we passed the straight line equation through the first point and the second point. We had 2 unknowns, a0 and a1, and it gave us 2 equations with 2 unknowns. We built the system of equations mp.linalgebra.solve, or Wikipedia help me with a 2x2 system of equations. Here's the solution. Great. So now, if you were given 3 points, x1, y1, x2, y2, and x3, y3, note here how we're changing our naming convention. In the past, it used to be y and x are the unknowns, right? And the coefficients are given. In this case, it's the other way around. We know the x and y data, right? And we're trying to find the coefficients. So I claim that with 3 data points, you can fit a full quadratic of the form a0 plus a1x plus a2x squared. Now you see the reasoning behind this nomenclature. A2 corresponds to x squared, a1 corresponds to x to the 1, a0 corresponds to x to the 0. Okay? So given 3 points, I want you to derive the system of equations that we need in order to solve for a0, a1, and a2. Those are the unknowns. We don't know what they are, right? But you have data about x and y. And you remember that any interpolating function, by definition, must pass through each and every point of the input data. So use that fact to your advantage to derive the system of equations that we need to solve to find a0, a1, and a2. Okay? You are not wrong, okay? You're correct. You're perfect. But I want you to write the equations down, please. Write the equations. Yeah, before we... You're right. I mean, this, in the end, is a system of equations, right? But just write down the equations. Before you get them in matrix form or any of that fancy stuff, just write down the equations. And there's a reason for that, Miles, because... There's a reason I asked you to do that, because what if I drop this coefficient? Or I put, you know what I'm saying? So it might trip you on the matrix, okay? Yes, exactly, exactly. So just like we did with the straight, write down the equations, okay, before you jump to matrices. Okay, write down the equations. The matrices are a representation of a system of equations, okay? Write down the equations. What are the 3 equations that we need to solve for the 3 unknowns? So now we're trying to fit this formula into 3 points. Okay? Good. Perfect. Just write the equation. I'm not asking for a solution. Just write down the equations. Okay? Good. Good. Perfect. Try it down, even if you're looking at the slides.
Oh, no, I
Try, yeah, and then verify it. As long as you practice it, because there are so many ways to trip that answer. Okay? Yes.
y1 of x equal to this with subscripts along the x, and y2 of x is equal to the same thing. Okay.
Yeah, but be careful. This is y1 at x1. Right? Yeah. Yeah. Or just put it y1.
Same with 2.
You got it. Okay. Any takers? First equation. Ethan.
Y1 equals A0 plus A1 x1 plus A2 x1 squared.
Okay, how did you obtain that equation?
If we take it from like the matrix form and multiply it over our coefficients, then
Which matrix form?
we not got it.
Nope. Nope.
Well, I figured that
I would highly recommend against doing it in the matrix form because there are so many ways I can trick you with that, and I will during an exam. So I always advise you to write down the equation because I can give you an equation and drop one term in it, and then it will mess up the entire matrix, okay? Okay, so what Ethan did essentially took the equation, the model, if you want, that equation, A0 plus A1x plus A2x squared, and applied it at x1, y1. So if you apply it at x1, by definition, it should return y1. We want it to return y1. It has to pass through x1, y1. Second equation.
Y2 equals A0 plus A1 x2 plus A2 x squared.
A2 x2 squared. Correct. Yep. It's taking that same equation, passing it through the second point. Okay. Third equation, same thing. Take the model, that quadratic, and apply it at x3. You apply it at x3, you simply plug in x3 on the right-hand side, and the left is going to be, by definition, y3. Okay? So now we have 3 equations and 3 unknowns. The question is this system a system of linear equations or nonlinear equations? Whoa, that's nonlinear. All right, who says nonlinear? This is exciting, okay? Okay. All right, we got like half. Both of you count as one vote. Okay, so we got about 10 saying nonlinear. Who's saying linear? Okay. Okay, so
I don't know that yet. That's my guess. Can they be my guess?
Oh my gosh. Wait, you're right. Oh my gosh, you're right.
okay, so let's remember, what did we say about a nonlinear equation? Does the variable of interest or do the variables of interest show up linearly or nonlinearly? What are the variables of interest here? A0, A1, and A2. Not x1, not x2, not x3, not x1 squared, not x2 squared. For all I care, they could be under logarithms of x1 to the power 1 million. It's a value. It's a number. The variables of interest, A0, A1, and A2, they are not exponentiated. They're not under a function. They show up linearly. And in fact, even if they were under a function in this case, I would call them a different name. If I had sine A1, I would call that A1 prime. Okay? I would just call that A1 prime. They are very linear equations. Thank God for that, right? Because now, look at this. It's a system of linear equations. We got our unknowns, A0, A1, A2. Our coefficient matrix is built from the input data. We know the x1, x2, and x3, right? And we know the y1, y2, y3, so we can solve this system and get a solution, okay? So now you start seeing a pattern emerge. And many of you wrote this matrix head on. And you were not wrong. But I strongly advise you to write the system of equations first, because the governing equation or the model equation, I can manipulate that in so many ways to mess up the structure of this matrix. So always write the equations and then convert to a matrix form. Now a pattern ensues. If you have 2 data points, you can fit a straight line, because a straight line has 2 unknowns, A0 and A1. With 3 data points, you can fit a quadratic, because a quadratic has 3 unknowns, A0, A1, and A2. And with the 3 data points, you're going to get 3 equations for the 3 unknowns. With 4 points, you can fit in a cubic, because a cubic has 4 unknowns, A0, A1, A2, and A3. And so on and so forth. Okay, ad infinitum. with n plus 1 points, you could fit an nth order full polynomial. So I had 50 points. I could fit a polynomial of degree 49. Okay? So when you have an entire data set, you can fit an nth order polynomial for each n plus 1 points. Okay? And the strategy is similar. You just apply that polynomial at each one of those points. You get a system of equations. You solve for the coefficients. You plug them back in the formula, and you do the interpolation. Okay? So we have n plus 1 unknowns. We need n plus 1 equations, and therefore we need n plus 1 points. Okay? So in general, for n plus 1 data points, we can fit a general polynomial of order n. By general polynomial, and pay attention to this, it means all the coefficients are there, a naught plus a1x plus a2x squared plus a3x cubed, and so on. There might be polynomials I'll ask you to do, fit a naught plus a3x cubed. That only needs 2 data points. Okay? Not 4, only needs 2 data points. So pay attention to that. Okay. Again, like an interpolating function, an interpolating polynomial by definition must go through each and every point of the data used to build the polynomial. And in general, if you write a polynomial using the summation form, summation of a k x to the k, and k goes from 0 to n, so that gives you a naught plus a1x plus a2x squared, etc. Then you're going to produce a general system of equations, which is many of you put in this matrix immediately. And that's fine when you have the full polynomial. But I always advise you to write down the equations first. Make sure you got all the terms ready there. OK, so now the idea is, now first the question is, can we do this? Do we know how to solve this? Absolutely. We know how to build a matrix. We know how to use numpy.lin algebra.solve. So we can invert this system for the coefficients, then take the coefficients, put them in the model equation, and then do the whole thing. Okay? But we're going to use built-in Python routines to do that, all of that for us. Ethan.
So if we're trying to get an equation for a line, will it always be most accurate if we use the highest order of equation possible?
That's a great question. We're going to address that once we start working with data. It turns out that high-order polynomials, anything beyond order 3, is a horrible idea. They become highly oscillatory, as we will see in some examples. And there's another alternative called the cubic splines, which is what we're going to prefer in the end. Okay? But the mechanism is very important to know, because once we switch to what we call a different basis functions, other than x squared and x cubed. What if I had sines and cosines in there? We can build crazy interpolants using the same methodology. Okay? But we build step by step. Okay. So now the idea would be to first obtain the polynomial coefficients by solving the system of equations. We know how to do it. Okay? But we're going to use built-in Python routines to enable us to just get those coefficients. And then once we have the coefficients, we plug them back into the polynomial and then evaluate the polynomial anywhere we want. OK, ready for some Pythonification? All right, we'll see. Unlike interp, we need 2 functions here to be able to do a polynomial interpolant in Python. Those are polyfit and polyval from NumPy. Okay? Polyfit, as the name designates, is going to fit a polynomial to a bunch of data. And polyval is going to evaluate that polynomial at any desired data. There's a reason why they split those two into 2 separate functions. Okay? But we're going to work with 2 steps in this case. So the first one is you're given data xi and yi. Okay? You call polyfit, you give it xi, yi, input data, just like temperature and density, like we did earlier, or hours and temperature for the other example. Now you have a third parameter over here, which is deg, stands for degree. This is the degree of the polynomial. In this chapter, For n plus 1 data points, you put degree n. Anything other than that is not going to do interpolation. It's going to do something called regression, which we will learn in the next chapter. But for now, you have 50 data points. You put degree equal 49. Okay? That is going to give you interpolation. Okay, so that covers xi, yi, and degree. Now this returns what I call p, a variable p. This is the vector of coefficients of the polynomial. Remember, we're solving for a0, a1, a2, a3, all the way to an, right? So this returns a vector of coefficients, but in reverse order. So the first entry in that answer is going to be an, the nth coefficient. So an x to the n, to the coefficient of x to the n, and so on. Now, once you have the coefficients, p, next you call polyval. You tell Python or NumPy, I want you to evaluate a polynomial with those coefficients p given as the first argument and evaluate them at xe. Just like before, xe is the value at which you want to evaluate, do that interpolation. It could be a single value. It could be an array of values, just like when we did with the temperature. Okay? And what is it going to return? It's going to return what we called ye, which are the values, the interpolated values. Okay? All right, so let's go and continue working with our data in that same notebook. Okay, let's switch back to Python. Look at that, polynomial interpolation. Let us now attempt to do polynomial interpolation on this data set, the data set for air. Okay, so if you recall, we had defined way up here temperature as our xi data, our independent variable, and density rho as our dependent variables. So now we're going to try to use a polynomial interpolant, okay, a full polynomial interpolant to interpolate those data. Okay, and we're going to take the entire data set. So from NumPy, import polyfit and polyval. Okay. Now the coefs of polyfit. Let me get my slides. It's always hard to get these slides over here. Okay. Okay. So polyfit takes 3 arguments at a minimum. The first 2 are the x and y input data. So t and rho. Okay. And then the question here is, and then the third one is degree. So the degree of the polynomial. Okay? Yes? Oh, no. No, for polynomial interpolation in this chapter, for degree, if you have n plus 1 data points, put n. Okay? Or n data points, put n minus 1. If you had 1,000 data points, put 999. Okay? So take the length of the array minus 1 for the degree of the polynomial. Okay? I see some question marks. Ask me. Exclamation marks, I guess. That, remember, polyfit is only going to return a collection of coefficients. You can print those and see them. It's just going to return the coefficients of the polynomial. It's, other words, going to solve that system of equations, okay, for the entire polynomial. Minus 1, exactly. Yep. So for the degree, just put length of t minus 1. Yes? Yes, great.
That's good.
That's good, because this is a bad thing what we're doing. Okay? Yep. It's a warning. Okay? We'll see what that warning means. That tells me you got it right, so. Okay. Okay, so let's do it. it takes xi, yi, and the degree of the polynomial. Now, if you look at the function signature, if you scroll down to degree, this is the degree of the fitting polynomial, okay? For this chapter, that degree is always number of data points minus 1. Once we do something else, it's no longer interpolation, okay? It's something called regression. All right, so let's do it. Let's do t and rho. And then we're going to put len of t, which is the number of points minus 1. Okay? Okay? So it gave me a warning. It says polyfit may be poorly conditioned. That's good. Okay? Because what we're doing is really bad. We're fitting a polynomial of order, let's see, what is len t? 18, 19? So len t. Yeah, so we're fitting a polynomial of order 18. So you have x to the power 18. Okay? That's not good at all. Just from a round-off standpoint, putting any number larger than 1 to the power 18 is just going to mess up, create a lot of round-off. Okay? So we're headed to trouble. But for the most part, it's going to be okay. So let's see. So first question is, what is stored in coefs? Okay? Coefs contains, if I print it, it contains a bunch of values. This is the coefficient of x to the power 18. It's such a small number, right? 10 to the minus 46. That's not even like, can the computer even compute that? It's a meaningless number. Okay? So that's a very awkward polynomial. But it's just the coefficients. That's what we got from the system. Okay? See a question? No? Agreement. Yes. Okay, good. Okay. So now evaluate the density at 412 and 415 kelvins. Okay? So now we're going to call polyval. The next step is to call polyval. You pass it the coefficients as the first argument and the values at which you want to interpolate as the second argument. So in the first argument, I'm going to pass in coefs. And in the second argument, I'm going to pass 412 and 415. Okay? And when I print it, it spits out some value. Okay? So let's see where these values fit in. Let's see. Okay, so I'm going to call this now YE. I want to plot them on top of the other one. Okay, so plt dot plot. Oh, looks like we ran out of time. I didn't even pay attention. We were so focused on this. Okay. Well, we'll have to continue next time. It's nice when time flies by and you're like so focused on it, but you guys can go. It's okay. We'll continue next time. Okay?